This scientific paper focuses on the elasticity of block copolymers with cubic symmetrical morphology using coarse-grained molecular dynamic simulation. The researchers investigate two typical cubic symmetry morphologies: body-centered cubic, BCC, and double gyroid, DG, which mimic thermoplastic elastomers and soft plastics. They study the effects of morphology, bridge fraction, the fraction of bridged chains, and deformation direction on the stress-strain curves of the block copolymers. In the case of the BCC morphology, the researchers find that the rubber elasticity is linearly dependent on the bridge fraction. They observe that the deformation of glassy networks with the DG morphology results in higher initial moduli compared to those with the BCC morphology. They attribute this difference to the loop configuration in the DG networks, which also contributes to rubber elasticity. The researchers note that the effect of deformation direction is insignificant in both the BCC and DG morphologies, which contradicts experimental results. They suggest that this discrepancy may be due to the limitations of the coarse-grained bead spring model used in the glassy state simulations. Block copolymers exhibit microphase separation, which can be controlled to modify the functionality and properties of thermoplastic elastomers. The authors highlight that thermoplastic elastomers consist of multi-block copolymers with dispersed glassy domains and a rubbery matrix. The glassy domains act as physical crosslink points, providing elasticity below the glass transition temperature, Tg, of the glassy domain. The fraction of bridged chains controls the overall elasticity of the material. Soft plastics, on the other hand, form continuous networks of glassy domains, resulting in complex elastic behavior combined with rubber elasticity. The authors also mention the potential applications of block copolymers with cubic symmetrical morphology, such as photonic crystals and nanoporous materials. They discuss previous experimental studies on the stress-strain behavior of DG morphology and highlight the anisotropic elastic properties observed in those experiments. However, they note that their simulation results do not fully capture the anisotropic behavior observed in experiments, which they attribute to the limitations of the coarse-grained bead spring model used in the simulations. In conclusion, this paper presents a study on the elasticity of block copolymers with cubic symmetrical morphology using coarse-grained molecular dynamic simulation. The researchers investigate the effects of morphology, bridge fraction, and deformation direction on the stress-strain curves of the block copolymers. They highlight the differences in the elastic behavior between BCC and DG morphologies and discuss the limitations of the bead spring model used in the simulations. Stress-strain curves for BCC and DG morphologies with different bridge fractions. The stress-strain curves for block copolymers with BCC and DG morphologies were obtained through uniaxial deformation simulations. Different bridge fractions were considered to investigate the effect on the stress-strain behavior. It was observed that the deformation of glassy networks with the DG morphology resulted in higher initial moduli compared to the BCC morphology. This suggests that the DG morphology is more rigid and resistant to deformation. Additionally, the rubber elasticity of the BCC morphology was found to be linearly dependent on the bridge fraction, while the dependency was weak in the DG morphology. This indicates that the loop configuration in the DG networks also contributes to rubber elasticity. The effect of deformation direction on the stress-strain curves was found to be insignificant for both morphologies, which is inconsistent with experimental results. This discrepancy may be attributed to the limitations of the coarse-grained bead spring model used in the simulations. Mooney-Rivlin plots for BCC samples. The Mooney-Rivlin plots were generated for the BCC samples to analyze the elastic behavior. The plots represent the stress as a function of the nominal strain. It was observed that the stress-strain behavior followed the Mooney-Rivlin equation, which is commonly used to describe the mechanical properties of elastomers. The coefficients C1 and C2 of the Mooney-Rivlin equation were determined from the linear region of the plots. C1 represents the crosslinking density in the rubbery state, and C2 represents the nonlinear elastic behavior. It was found that C1 increased linearly with the bridge fraction, indicating that the bridged chains contribute to the crosslinking and rubber elasticity. On the other hand, C2 remained relatively constant across different bridge fractions, suggesting that the nonlinear elastic behavior is independent of the bridge fraction. Mooney-Rivlin coefficients C1 and C2 for BCC samples. The coefficients C1 and C2 of the Mooney-Rivlin equation were analyzed as a function of the bridge fraction for the BCC samples. It was observed that C1 increased linearly with the bridge fraction, indicating a proportional relationship between the cross-linking density and the bridge fraction. On the other hand, C2 remained relatively constant across different bridge fractions, suggesting that the nonlinear elastic behavior is not significantly affected by the bridge fraction. Snapshot structures of BCC samples at strain equals 3. The snapshot structures of the BCC samples under uniaxial deformation at a nominal strain of 3 were visualized to understand the deformation behavior. It was observed that the bridged chains in the triblock copolymers were stretched, while there was no significant stretching of the chains in the D-block copolymers. This difference in deformation behavior can explain the higher stress observed in the triblock copolymers compared to the D-block copolymers. The study investigated the elasticity of block copolymers with cubic symmetrical morphology using coarse-grained molecular dynamic simulation. Two morphologies, body-centered cubic (BCC) and double gyroid (DG) were considered. The effects of morphology, bridge fraction, and deformation direction on the stress-strain curves were studied. The results showed that the deformation of glassy networks with the DG morphology resulted in higher initial moduli than those with the BCC morphology. The rubber elasticity in the BCC morphology was linearly dependent on the bridge fraction, while in the DG morphology the dependency was weak due to the contribution of the loop configuration in the networks. The effect of deformation direction was found to be insignificant in both morphologies. However, the results were inconsistent with experimental findings, highlighting the limitations of the coarse-grained bead spring model in the glassy state. Overall, the study provides insights into the elasticity of block copolymers with cubic symmetrical morphology and emphasizes the need for more sophisticated models to accurately capture their behavior. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.